Here's an equation in two variables. The solution set of this equation has multiple solutions in it. They are ordered pairs. And typically, we can talk about the graph of that solution set. And oftentimes, the graph of the solution set of an equation in two variables will make some geometric figure with which we are familiar. Sometimes they'll make strange figures that we're not familiar with. But we can learn a lot about those geometric figures. We can learn a lot about the graph of a solution set of an equation in two variables if we will simply analyze it algebraically in terms of symmetry and intercepts. So let's find the intercepts first of this equation in two variables. Where would the curve of the graph of the solution set of this equation, where would it cross the x and y axis? Remember, to find the y-intercept, we let x be 0 and solve the resulting equation for y. So if I want to find the y-intercept, I'm going to let x be 0 in this equation. Well, 0 squared is 0. So here's the equation we have, y squared equals 9. That's a quadratic equation that I can solve by applying the square root property. Simply take the square root of both sides. Remembering I have to account for both the positive and the negative square root. So y equals plus or minus 3, which tells us that we have two y-intercepts. They would be the points 0, negative 3, and 0, 3. To find the x-intercept, we do the opposite. We let y be 0 and solve for x. And aren't we going to get the same solutions for x, 3 and negative 3, when we take the square root of both sides here? So that tells us there are two x-intercepts. The points negative 3, 0, and 3, 0. So graphically, the picture, the graph of the solution set of this equation would cross the y-axis at 0, negative 3, 0, 3, and would cross the x-axis at negative 3, 0, and 3, 0. Now let's look at it in terms of symmetry. Remember, to test symmetry, we replace, if we're going to test symmetry with respect to the y-axis, we replace x with negative x. And see if this expression is equivalent to the original expression that we had. And it is, because the square of minus x is equal to the square of x. So we can get directly back to that equation, which tells us that the graph of this equation solution set would be symmetric with respect to the y-axis. Then to test for symmetry with respect to the x-axis, we replace y with minus y and see if we can get back to the original expression. Again, the square of minus y is the same as the square of y. The square of a negative number is the same as the square of its positive counterpart. The square of negative 3 is the same as the square of positive 3. So that gets us back to the same expression. So here we've shown we have symmetry with respect to the y-axis. Here's symmetry with respect to the x-axis. And to test for symmetry with respect to the origin, we replace both x and y with minus x and minus y. Well, again, by the same argument we've just given, these two values are equal to their counterparts x squared and y squared. So this is an equivalent expression telling us we have symmetry with respect to the origin. And that means, so here we have this graph that these are all intercepts where the x and the y values are 3, and any point here, there's a counter point a symmetric point here because of symmetry with respect to the y-axis. Any point here has a symmetric point here because of symmetry with respect to the x-axis. And any point here also has a point over here because of symmetry with respect to the origin. And we end up with a circle. And indeed, the graph of the solution set of that equation is a circle. It's a circle centered at the origin with a radius of 3. Because 3 squared is 9. That's the type of thing we can learn about the graph of the solution set of an equation by analyzing its intercepts and analyzing symmetry.